Okay, so all right, let's talk a little bit. So last time we talked about, what did we talk about? Yeah, so the things relating to the Lebesgue differentiation theorem and its proof, which requires this thing called the Hardy-Littlewood maximal function, right? So I take supreme over averages of balls. And in order to prove these things, I needed a version of Vitali to to pick which collection of balls I can work with, and then we showed this Hardy-Littlewood maximal inequality, right, for the weak, so L1 to weak L1 bound. Okay, and then that proves the Lebesgue dominated convergence theorem if I have this kind of bound by comparing L1 low functions to continuous functions. Okay. So the next the last little part is more on, so previously it was all on things which are pretty irregular, so functions which are just pointwise almost ever defined, right? And have some property where they're not too large. Now we're going to start to dig into a little bit more what like continuity, what aspects of continuity are. So the first version of this is absolute continuity. So it's a version, it turns out to be equivalent in 1D to having the fundamental theorem of calculus hold. So in order to talk about that, we have to first define what bounded variation is. So here I consider a function which just goes from some closed interval to R. So everything's in R. And now what I do is I pick a partition of this interval A to B in terms of this is x1, x0, and then B equals xn. Right, so my partition is this gamma. Okay. And then with this partition, I can define this S gamma function, which is defined to be how much I jump, how much I move between each of these points. So if my function is above this, right? So I have some sort of function that does this, then the difference between this point and this point is like 0. The difference between this point and this point is also around 0, but the difference between this point and this point is like whatever, 1 or something, right? So I'm counting up how much I jump. So if for every partition I could possibly pick, this guy is finite, then I say it's to be a bounded variation. So this is a very kind of weak form. It says my function doesn't oscillate too much on this interval. Okay. So things that have bounded variation are nice. The things that have like the next version up are even better. So really it's kind of the same constraint. I'm going to subdivide some interval AB, and I'm going to ask that f has some property on this interval when I start cutting it up. In particular, what it says is for every epsilon greater than 0, there exists a delta such that for any collection of non-overlapping subintervals, so what I'm going to be thinking of as is things that look like this, right? What I do is if the condition that the sum of all of these non-overlapping intervals, so the total volume of each of these chunks is less than some delta, then I want that the collection of all of them is also less than epsilon. So when I measure the variation, it's less than epsilon. Okay. So an example of something which is not absolutely continuous is, so, okay, maybe we pick, yeah, okay. So an example of something which is not a function, which is not, and then usually people just call it AC for absolutely continuous, is the Cantor Lebesgue function. So what this function is I take the set, the Cantor set. So this is one step of the Cantor set. And what I do is on each of these chunks, I start in 0 and I end at 1. And in the in-between, I fill it with this kind of bridge, right? If I do that. Yeah, okay. And so if you think about how the Cantor set looks, right, it's basically a infinite, some sort of fractal where each of the pictures of the set kind of looks like these two intervals, right? So what's happening is I'm squeezing in almost infinitely many little jumps of size 1 into it. So it's a continuous function, but it's not absolutely continuous. Okay. Is this clear kind of what I'm saying? I'm not going to give a proof that this it does not absolutely continuous, but I think it should be apparent that if I take any collection of these AI/BI subintervals and I look at the this Cantor-Lebesgue function, I'll pick up infinitely many little jumps, right? And if I end up checking this condition, I can show that I don't satisfy. In particular, no matter how small I pick delta, I have infinitely many subintervals, so I pick up something at least more than my epsilon. Okay. Okay, so this is absolute continuity. It's things which are continuous. So things which are absolutely continuous. If I pick one subinterval, that implies that it's continuous, right? So absolute continuity implies continuity, but not the other way around. And this Cantor-Lebesgue function is an example. Okay. So it ends up being very nice that in general, if I have an absolutely continuous function, then f prime, so the limit of the difference quotients of f, exists for almost every base point. Moreover, f prime is integrable, and I have the fundamental theorem of calculus that holds. So in general, this is again a theorem. I don't want to show it, but in general, we have only the inequality. So if I have, for example, a function which is only continuous, so let's say like this, so ax is less than or equal to. An example of this, again, is the Cantor-Lebesgue function, right? So the Cantor-Lebesgue function kind of looks like some crazy step function. So if it's Cantor-Lebesgue, the construction which we had before, if I iterate this construction, I'm constant on every piece of the Cantor set. Actually, I think I did this construction backwards. Let me think.
Yeah, I think you're constant
On the
on every
complement.
sides the Cantor set because it's a
Yeah,
function that grows only on a set of measures 0.
yeah. So I have this picture backwards somehow. Because when I start subdividing this, right? So this is the line is on the complement of the Cantor set. So instead, let me change the picture. Really, what it's supposed to look like is something like so. It's going to be like this. So this is a much better picture. So the Cantor-Lebesgue function looks like something that does this, where on every chunk where I'm on the Cantor set, so this is the first iteration of how I construct the Cantor set, I'm going to have slope, let's say, whatever the distance is from here to here. So some bounded slope. And then when I'm outside the Cantor set, I'm constant, right? So what I'm doing is in the Cantor set, and let's say I subdivide again in this chunk, what it'll look like is I go blue. So if I do the Cantor construction again, I'll go like this, and then I'll be constant, and then I'll go like this. Yeah, sorry about that. This is what it should look like. And here, I'm just going to continue up this point. So we'll go like this, constant, and this. So I'm slowly adding more and more kind chunks to it, or little variations to it. Okay. Okay, so if I have that, you can check that if cant f prime here equals 0 on the complement of this set, where the C is the Cantor-Lebesgue set, right? So actually I have for Cantor-Lebesgue, it's 0, but when I check, I go from 0 to 1 just by the construction. So this guy equals 1. So this function is kind of a good, helps you remember which direction it goes, right? So really the issue is if my derivative is 0 often, then I don't have equality here, right? Okay, and in the exam, I find this is it changes, depends on who writes the exam, but this concept is less kind of focused on. It's more on like that the definition in some sense. And if you've seen the proof of this theorem, it's wonderful. But you won't need to know the minutia. Okay, is there any questions about this notion of absolute continuity? Okay, cool. So for next time, I'll talk a little bit about functional analysis. But this is kind of just the extra stuff that you it's more probably on the topic of the applied 1 exam. So like the applied 1 exam here is just functional analysis in some sense. But we'll go over that next time. What I wanted to do is just solve a few problems. So what I'm going to do is I'm going to put this up and maybe give us like a minute to look at it, just so we're all on the same page of what this is. And then we'll just go through and solve these one by one. And so I picked up 4 today to do. So let's give it a minute break. I'm going to make a coffee real quick, and you guys should try and solve this problem. Okay, I think that's about enough time to just get a feel for the problem. Let's see. Okay, Flavio, what are your thoughts on how to do this?
So I'm thinking the one way, but we can just write the definition of like convolution, and then we'll have an integral with a product of f at x minus y times k to the n g of ky in the y. And we want to show that this converges pointwise to 0. And
Yes.
I don't know, my how I would go about it is like k to the n times g of ky
Mhm.
should go to 0. So basically we want g of ky to go faster to 0.
Mhm.
And maybe we can use some sort of Chebyshev inequality to try and argue about that, or
Yeah, I think,
not
okay,
really
so
sure.
yeah. So that way, so you're trying to use this in some
Using
way.
that g is bounded.
Yes.
Is-
So I like it, but the idea, I think, if I was to have just g as a positive function, um, this guy would not go to 0 because it
Yeah, so
starts to
since
look
the
like if I
integral,
go like this, where this is of size k. So this is k to the n, and this is of size k. So in general, it looks like this if a f is positive, but what we're having to use is this condition here. So this is actually a fairly common thing when you see convolutions. You'll often see it written a different way. But the trick with convolutions is basically if g looks like this function, and
yeah,
I integrate it against f, it's somehow like picking up whatever around x is. So it's kind of like averaging around the point x. Okay, but for us, we actually have something that's not positive. It does something um, like this, for example. So this is our g. Um, so let me just give one hint. If I know the integral of g is 0, I can rewrite this integral like this. And so this is often the trick you see with these types of things. This is somehow uh, how do I say this? This is like mollifying towards some sort of class of mollifiers. Um, but if I write it like this, and I'll just write gk of y, dy, right? So what we're using here is when I just freeze x, right? And I look at this integral in y, I can immediately use this condition. So these guys are equal, right? So this term is just 0. But the reason I want it is it allows me to compare x at the single point to x around whatever this kind of average is. Okay. So yes, let's see. How about Iris? What do you think? What can we do after this step? Let's say I write this. This is kind of the first step. So if I want to show that this whole quantity goes to 0, what should I be thinking about?
Wait,
Sorry.
sorry. Do you mean to write a k to the power of n in the second line?
Yeah.
Wait, it's in the G sub K of Y, right?
Yeah, it's in G sub k. So
Oh,
I'm just rewriting it. But yeah, maybe we put it back and see what happens. I'll write it like this, ky again. But yes,
No, I guess I maybe we could split the integral up into we're integrating near the point X versus far away from the point X.
yes, exactly. Yep. So in order to do that, I'm going to do a little trick. If I put absolute values, things don't change too much, right? So I can make absolute values here. But yes, that's exactly the right idea. So if I do this and I rewrite my integral, often you'll see people write, okay, let's pick some delta, right? Y less than delta of this guy, f x minus y minus f of x. And then I'm just gonna write this because my hand hurts. Okay, so this is very common. This is a great trick to do in some sense because, as I was saying before, you want to look locally at what happens. So if y is close to x, y is small, so in this part, I can somehow use that these guys should be close in L1, right? Because I'm just translating my function a little bit. So they should be kind of pretty close. The other part, I somehow have to use that GK goes to 0, right? So there's really two behaviors I have to focus out. So one is, okay, I got to use continuity somehow. The other is I have to use boundedness of some quantity. So let's do these part by part. So I'm going to write this as I1, and then there's going to be an I2. So I1, if I change, I want to do that. Yeah, if I change variables, so this is the part where these 2 points are very different from each other, right? So f of x minus y and x are different. They're greater than delta apart. Or they're just, yeah, they're greater than delta apart. So I somehow need to use the g decays if I want to show that this thing goes to 0. So I'm just going to use that f is bounded here. So this is 2 times L infinity norm of f. And then it'll be the integral of y greater than delta of gk, which I'm going to, I guess now write as k to the n gky dy. And then let's do the following change of variables, right? So if I let z equal k times y, dz equals, if I'm working in n dimensions, there'll be a k to the n dy, right? So it's exactly this guy. So just rewriting it, I have f L infinity integral, and then y becomes z over k. So when I replace y here, I get a z, and then there'll be a k delta. And then this will just be g of z dz. Is that clear to everybody how I did that? Okay. So now I'm taking k to infinity, if you remember. And I know that g is integrable from my problem. Right? So I have g is an integrable function. Okay. So can anybody tell me how to show that this I1 goes to 0?
Oh, dominated convergence of GZ times the indicator of Z is greater than K delta.
Yeah. So let's do that. So L infinity, this is the integral over the whole thing. Okay? Characteristic function of Z greater than K delta of Z, G of Z, dz. This is R to the n. And I know by dominated convergence, this guy is always bounded above by G, right? Because I'm only multiplying by a function which is either 0 or 1. And I also know that as I take this guy, limits towards the empty set, which is 0. Okay, so if I get that, I know that this guy goes to 0. We're good. I'll just write converges to 0. And then apply dominated convergence. Okay. Great, so that takes care of the part where I can use the decay of GK. Okay, so let's do the I2, the second part. Okay, so for I2, let's recall what it is first. So I2 is the integral where I am close to delta, right? And then it's going to be, I have to utilize that this difference makes sense. So this should be x. GK of y dy. Okay, so I'm just going to use that this guy is bounded. How do I want to say this?
You can do Holder's inequality.
So Holders is kind of it's bounded.
Oh wait, Yeah, it's actually a little bit yeah, sorry.
Yeah.
That doesn't quite work. Yeah, the way that I just worked out this problem was by approximating GK by a bounded, compactly supported function. Or approximating G, but I don't know how to translate that to
Yeah,
garbage.
so the thing I'm seeing is if I have a k to the n, k, why? Right, as I take k to infinity, this guy kind of blows up. So it's not actually bound, gk is not bounded to k, g is bounded, right? But let's still continue and see what happens. If I do the same change of variables, where I look at z equals ky, dz equals k to the n dy, and I'm allowed to cancel this guy. So if I do that, this I2 is going to be y less than delta f of x minus y, f of x. And then here I have, so instead of y, I have z over k. I want to do this. You know,
Wait, the other part is GK, right?
yeah. Yeah, do you see it? I'm worried about it blowing up as I take k to infinity.
Yeah,
It's just plain G, right?
This one should just be g. If I do this, so this is z over k. And then this will be y less than z less than k. Let me think. Okay, so this guy is bounded by our problem. So I
is that
can,
actually in the problem statement that G is bounded?
it might not be. G is integrable. Yeah, f and g are bounded measurable functions.
Okay,
So if I do that, now I can pull out g. This is g in all infinity. And then I think I want to change variables. No. Let's do this. Okay.
yeah, if G is in L infinity, then GK is also in L infinity, so you actually never needed that change of oh wait, no, sorry,
No,
never
it's
mind,
not.
never
The
mind.
scaling's wrong. It's L1
Well,
scaling.
you have to, yeah, never
Okay,
mind.
no worries. Okay, so I have this. Okay, I'm back on the right track. Great. Okay, actually, it ends up being that k to the n is not really
Yeah,
that
you,
much of a problem
I think you
because
actually,
if I go back and change variables here, yeah, I'll go back to y. Sorry, in some sense you didn't need to do this, but if I go y less than delta, there's a y. This is a y, but with a k to the n. Nope, I don't want to do that. That's not what I'm saying. Instead, okay, this is too many variables. This is do w. Okay, w, dw. This is really what's happening. So when I'm integrating this guy, right, the set where this happens is this. C over k is less than delta.
Can we approximate f with continuous functions now?
Yes. That was
Couldn't we
my,
just apply dominated convergence with like delta going to 0? Because if delta's one,
yeah,
then
yes, okay. Yeah. So
No, at this
let's
point, you
see
do a
again.
big integration.
I think either of these could work. But yeah, the way I was thinking is dominated convergence. Or sorry, the Lebesgue differentiation theorem. Getting confused. Okay. Okay. Let me just say there's many different ways to show that this goes to 0 by convergence or differentiation theorem, right? Because this is somehow like a ball of radius delta. Right. Okay. Okay. There is some trick. Okay, I'm just going to leave this because I don't want to spend too much time on it. So the trick here, pick delta correctly. So let me just say, let's keep it at, yeah, okay. Yeah, I'm just because I'm struggling with this at the moment. Let's just go back to this. So Z is less than K. Okay. So I'll just write it like this, delta of K. So I'll let you guys figure out how to do that because I don't want to spend too much time on it. But in some sense, what you're trying to do is to use the fact that if F is integrable and then I integrate over some small ball, right? So this is saying, okay, I'm within delta of my ball. Then I should, this guy should converge to 0, right? Okay. I think I can pick it depending on K. Yeah, okay. Okay, well, is the big argument clear? Really, the main trick, if you guys see this on an exam, I don't know if it's a trick, it's kind of a common thing, is you have to reintroduce, you have to use that the integral of g is constant. The reason it's k to the n, g of k times y, is normally that it's normalized. So when I move k around, the L1 norm of k, gk doesn't change, right? Okay, and so the next trick is once I introduce this f, then I have a quantity which I can play with in terms of a difference of f. Then I pick the part where I'm greater than, so I'm outside of some ball, and then I'm inside some ball. And each of those I do two different things. The one where I'm outside of some ball, I use that g is integrable, and I'm scaling it in this particular way, right? For the part where I'm within a ball, I have to use the f is somehow continuous with respect to the thing I'm taking. And the way I would think about that is you either use dominated convergence, you use density of continuous functions, or you use the differentiation theorem. There's a lot of different ways you can justify that. Okay. Yeah, sorry about the messy explanation here. I just don't want to say anything wrong, but I think if you just sat down and stared at it, you could figure it out. Okay. I'm going to go to the next one. Let's see. So I'll just read this one. So if I have fk as a sequence of L1 functions on the interval 0, 1, and they converge to an f pointwise almost everywhere, show that fk minus f, so fk converges to f in L1, if and only if, for every epsilon greater than 0, I can find a delta such that the integral of fk over this set A is less than epsilon. So in some sense, this is like absolute continuity, right? This condition. So here I can say the super over K, for example. It's some sort of condition. I mean, it's saying that no matter what set I pick, as long as it's measurable and has size less than delta, if I integrate this sequence of functions along it, I know that I don't pick up too much mass by any of them.
Yeah, isn't this called uniform integrability or something like that?
Yeah. So this is uniform integrability. Yeah, it's a version. Okay. So how would we show this direction? So what I want to show is that I assume fk goes to 0, fk minus f goes to 0, L1 0 implies that for epsilon greater than 0, there exists a delta such that a fk is less than epsilon. Okay. If a is less than delta. Okay. So let's start working this out. Okay. Anybody have any ideas?
Yeah, I mean, I would wait, shoot, I just totally had a brain fart. One second.
You're good. So I have
Oh
to
yeah,
say,
okay, so I would take it for large enough F.
Mhm. So
Um,
k large enough, k greater than equals to k.
that the L1 difference is less than like some fraction of epsilon. I don't know the exact number off the top of my head. Sure.
Yeah, that works usually. Okay.
And so then we really only need to estimate that this holds for F. This condition
Mhm.
holds for F up top because we can just take the
Let me write out that step. I see what you're saying. So if I want to look at this quantity, I can use triangle inequality, right, to get f k minus f, right, plus integral a of f. But I know that this guy is bounded by fk minus f and L1 plus this. And this guy is less than or equal to like epsilon over 100 plus integral a of f. That's what you're saying, right? Okay. So
yeah,
now that I
and
have one function, yeah, what do I do?
so now what I do is I would approximate by a bounded function.
Okay.
And then from there we're done because we have the tail controlled, and since the initial part is in L1, we just take it over the tail in the initial part.
So let me write out that carefully. So there exists a g, which is a continuous function and bounded on 0, 1, such that f minus g in L1 is less than epsilon over 100 again, say. So this guy is less than or equal to like epsilon over 50 plus integral a of g, where g is now a bounded function, right? I just did triangle inequality one more time. Now I know that, okay, yeah, this guy is less than or equal to epsilon over 50 plus, and then whatever the norm, this guy is now infinity times whatever the measure of a was. Okay, and the reason you can do this for f is because there's no k dependence here, right? So if I go through and I look at this, I have to pick delta less than something which depends on epsilon, and it depends on G, right? If G had a K in it, if there was some K here, I couldn't do this. But to finish the argument, what I want to say is pick delta less than 1 over, so epsilon over 50 times G no infinity. Okay. So that's the first direction. So that's forward. Okay. So is that part clear to everybody what this argument is? Okay, great. For the other direction, what do we want to show? We want to show that if I have this condition, so if for every epsilon greater than 0, there exists a delta such that a less than delta implies the sup over k of fk over the set A is less than epsilon. So if I have this condition, then fk minus f in L1 goes to 0. Okay. Wonderful. Okay. So does anybody have any ideas of how to do this? So let me give,
Yeah,
maybe a little hint first. The way I'm thinking about it is, let's, for example, so let epsilon be, use the condition for epsilon equals 1, so see what happens, right? So what this means is there exists a delta such that if A is less than delta, then I know that the supremum of these guys, fk, is less than 1. So I'm working on this is the space, is my space. What I can do is I can look at, how do I say this? Okay. So there's a
Wait,
small
sorry.
reduction.
Can you just go up to the question one more time?
Sure. The question statement,
Oh, okay, it's over 0, 1.
it's over 0, 1. Yeah. So
yeah,
the way, there's one reduction, and this is like a little fun trick I like. If I have this, so what I'm trying to do is just get just basic control over these quantities. One of the things I would like to see is the absolute value here be inside and on the function, just to try and control the thing. Now this ends up being kind of a simple reduction because I can define for any A, I can define A plus to be this set. This depends on. Yeah, this guy is greater than 0. Okay. Okay, so if I define these A plus, which depends on K, if I do this, right? Actually, this condition holds for any A less than delta. So if A is less than delta, A plus is less than delta, and I actually don't have to worry about the K. So what this shows is, if I apply this to these two sets, then I get the sup over K of the integral of A fk is less than or equal to 2, right? Because I split this set, I have one chunk which I apply this to, and then the other chunk.
so basically you've replaced the condition involving the absolute value of the integral with the condition involving the integral of the absolute
Yeah.
value. But
Yeah,
this works for any epsilon. You go from epsilon to 2 epsilon.
Yeah, so let's think about that. So yeah, let's just replace this by epsilon and 2 epsilon. So let epsilon be positive. And I have 2 epsilon here. Okay. Well, if I have that, let's see. The quantity I'm trying to control is fk minus f in L1. Right? So I want to say okay. So this is going to be the integral from 0 to 1 of this guy. Okay. Okay. So notice that if I have, so I fix a delta. This is why I fixed epsilon to be 1. Okay. So
Yeah.
if I fix epsilon to be 1 again, then delta is fixed, right? And what this shows is with some delta fixed, I can pick, for example, a j to be the intervals like intervals of size less than delta, right? And so there's going to be, and I want the union of AJs to cover 1 to n covers my set 0, 1. So in particular, I need so n, which is the number of them is greater than 1 over delta. So if I do this and I'm basically, I apply my condition n times, right? Then what I get is that the sup of 0, 1 fk is less than or equal to 2 times, well, how many intervals did I have? I had n intervals. Okay. So this gets me control over the whole thing. So I know that these guys are all finite, bounded. What I can also do is Fatou's lemma. So lim of fk, I actually know is less than or equal to lim of integral of fk, right? Which I know for this whole set is less than or equal to 2f. But I know from the problem statement that this is going to be f. So this implies that f is in L1, which I don't think we knew beforehand. Yeah, so we didn't actually know that f was in L1. Okay. So I've shown that f is in L1 by Fatou. Now, what I want to do is look at this difference again, fk minus f. And if so I know that these are a sequence of L1 functions. I
Now
can
we can
assume,
use deterministic convergence, right? Because we have pointwise convergence.
so the issue here is that because I have pointwise convergence doesn't mean that all of these functions are bounded in with respect to like this envelope story. So like, just because I don't know something like this is not known, right? So I know that, okay, my L1 norm can't grow in some sense, but I don't know pointwise what's happening. So I cannot apply dominated convergence directly here. Okay. So cannot, no dominated convergence. Okay. Just as an aside. So I like where you're thinking though. Dominated convergence usually works for these things. Instead, let's do the following. Let's say I look at this quantity and I rewrite it like there's going to be a set A, some arbitrary set, and then there's going to be an A complement. Okay. So I know that if A is less than delta, I'm great, right? Because let's see. If A is less than delta, if A is less than delta, then integral of fk over A is less than 2 epsilon, right? That was our thing we showed above. It's this guy.
Sorry. Can I ask you again? Didn't we
Sure.
show that the slope of the integral from 0, 1 of the absolute value of fk is bounded at 2n for all k? Doesn't that show that all the fk's are bounded by 2n and also f is bounded by 2n, and so we can apply dominated convergence? Maybe I'm losing.
It's what you're saying is correct, but all of these have integrals on them, right? So there's an integral here. So what I'm saying is the total mass of the thing is less than 2n. In order to apply dominated convergence, I need somehow local information, like locally what happens to functions. Yeah. So no, it's a huge distinction actually. And that's why these notions end up being equivalent of how much do I wiggle outside of sets, like my sequence, how much does these integrals kind of wiggle? And if it's not so bad, then I can actually upgrade from pointwise convergence to L1 convergence. Okay. Okay, so if A is less than delta, I know that, so I'm looking at this term here. I know that this happens, so I'm good. I also know that integral of A of fk, f, is also less than 2 epsilon. And this is again by Fatu. Right? Because if I do the same trick, if I look at this inequality, I get lim inf of f is less than or equal to lim inf of these quantities. And if I picked an A here, right, I know that these guys are going to be uniformly less than this. Okay. So these two, this ends up being a fine term to control. On the complement, right, I have to do something special. So on the complement, I do two things. On a complement, one is I approximate no. This is going to be throw it. Okay. Apply. I think it's Lucen's theorem. Yes. Okay. So what Lucen's theorem says, I think it's Lucen's, it could be Grove, is that if I have a sequence of functions which are finite valued, so here I can assume without loss of generality that this is finite valued, then this family of functions, I can pick a subsequence of them. Sorry, no. I can pick a small enough set such that on the complement, I get uniform convergence.
Oh,
right?
I think
so. Is that Egorov?
I think Lucent, it's like almost continuous, right?
Yeah. Okay. This is Egorov. I always get those confused. Something like that. I don't have my notes nearby, but to get uniform convergence. Does that make sense? So this is one of the first kind of theorems we went over in lecture. Double check the name of it because it's going to bug me.
It is Egorov's theorem.
It is Egorov. Perfect. Okay.
Okay, so a complement is sort of you choose that first is really what's going on, right? And then
yeah, really that's what you do. Yeah. So these problems, I find it's nice to write in pencil or have like a lot of scratch paper because the actual process of going through this is fairly nonlinear. It's like, what can I control? What can I get? And so for this, yeah, formally, if I'm to write it out explicitly, I would pick a complement first, right? apply Igorov, get uniform convergence so I can control this term. Right? And then on the complement, I get small measure, and then I can use my conditions that I have. So this is the condition of my problem, and this is follows from pointwise convergence in Patou. Okay. Okay, and so let's do one more, and then we'll meet in 1 week. So let's do this problem. So if h is a monotone function, let's assume h of 0 is 0, and h continuous. It doesn't say it in the problem, but I don't think it's actually true. It's not within the, I think you can assume this. Normally this is in context where you'll apply things like h will be the function f log f, for example, or something like this. Okay, so if I have this, I want to figure out how to write this integral in terms of the super level sets of f. Okay, so I'm just gonna, if you recall the layer cake formula, I think we proved it in lecture. What you end up doing is if I want to express integrals like this in terms of measures of super level sets like this, what you have to do is formally insert a integral, right? So then I can use Fubini and rearrange stuff. So what you'll end up looking at is f of x for any x is going to be this quantity. Right? This is just fundamental theorem of calculus. If it's, let's just say it's absolutely continuous.
Well, if it's monotone and it's continuous, then it should automatically be absolutely continuous. It's fairly easy to see from the definition.
Wait, also,
It's in
does it
the
assume that h of
function
0 is, oh, sorry.
So one at a time. Jacob.
Doesn't this assume that h of 0 is 0? Or
This
h
one
of f
assumes
is 0?
So this one assumes.
Oh, you just wrote that, sorry.
I just wrote 0. Yeah. So this one is this. I'm not sure if monotone implies absolute continuity.
I was gonna say, didn't the counterexample we have for absolutely continuous, wasn't that monotone?
Yeah, so our Cantor-Lebesgue function, let me see, is increasing. So it's not, yeah, so
Right, but if it's monotone and continuous, then
the Cantor-Lebesgue function is both of those. F is absolutely continuous. So part of the problem for some, especially if I've noticed if Caffarelli wrote the exam, he'll write things like this. I'm pretty sure he wrote this. But you got to kind of you got to figure out what the assumptions are. And so if you come across a problem in an exam where there's not enough assumptions, just run with it and see if I add an assumption, what can I do? Right? Sometimes, and that gets you points anyway. So let's just assume it's absolutely continuous and do what we want to do because the main part's the computation. So if I rewrite it like this assumes h of 0 is 0 and absolute continuity, but I get a nice formula. When I integrate this guy, dx, right? This looks identical to the argument I had before with the layer cake formula. So I can write this as the integral of the characteristic function 0 to f. This is the set where this is the set of y such that y is less than f of x. Okay.
yeah,
And
you're
then
right.
this is h prime of y dy. And then dx. Okay. Where this is going from 0 to infinity. Okay. So if I have this, I can apply Fubini because each of these is now independent of the bounds of integration. And so when I look at this quantity of y, h prime of y, dx, y, right? I can move this guy outside because it no longer depends. And then what I get is the integral from 0 to infinity of h prime of y, and then the measure of this set is y less than f of x, right? Which is our function g of y, so right g of y. So this is how you express this quantity. If I look at a function of my f, and I want to rewrite it in terms of the super level sets, I look at it like this. Okay. One last thing. I know we're a little over time, but I just wanted to show you this last problem. So the idea is I want to define something which is like a mean functional of f. And the goal is to check this inequality. So I take the p norm of this guy, 0 to infinity, and I want to show this. So there's a hint which I'd like to say, which is called the generalized Minkowski inequality. So what this says is if I have, in general, an integral of f of y dy, and this is an LP dx, I can do a version of triangle inequality, f of y. Let's say xy, f of xy. Right? F of xy. And this is going to be LP in dx dy. So if you recall, Minkowski's inequality is triangle inequality, right? If I have a finite sum, right, if this integral is a sum, this is obviously true by just iteratively applying Minkowski. It ends up being true that if I replace, a sum by a infinite sum, so an integral, the same result is true. So as an exercise, you guys should show this inequality using this one. Okay, is this the statement of like this generalized Minkowski inequality make sense to people? I'm like it's just doing triangle inequality, like absolute value, but if I have multiple variables, I do it like this, right? Okay. Great. So that's the end of the meeting. Now let me stop share. Okay.
Yeah, a monotonic continuous function is not necessarily